Hello and welcome to the Computer Vision Festival, hosted by the AI Accelerator Institute, a global community of over 400,000 AI leaders and practitioners, all striving towards one shared goal: inspiring the next generation of machine intelligence. With expert presentations on the festival agenda covering everything from space exploration on Mars to self-supervised learning, you're in for a treat. If you have any questions for our speakers or want to connect with them further, then ask away in the comments sections of the video and hear them answered at the end of each session in our live Q&As. If throughout the day you're loving the content, then be sure to check out the AI membership plans, where you can get access to exclusive content in the form of interviews, reports and articles. Access all areas passes to all past and future events. You can also join our Slack community, which is home to more than 2,500 fellow AI, machine learning and computer vision professionals, and is full of dynamic conversations and contributions. So if you're not already a member, come and join us today. Sign up using the link on the AI Accelerator Institute website. I want to say a massive thank you to all of our sponsors and partners for helping us to bring the festival to your screens today. Our amazing speakers for contributing some awesome content, and to you, our attendees, for joining us today. That's it from us, so go ahead, sit back, relax, and enjoy the festival.
Hi, my name's Cameron Cook, and I'm delighted to be here today presenting to you. I work for Airbus as an expert in artificial intelligence with a focus on computer vision. In particular, I focus on looking at how we can apply computer vision to solve some really challenging problems in manufacturing. I want to talk to you about a number of things today. Firstly, I want to talk about how we're using computer vision at Airbus to set the context, why I'm so interested in self-supervised learning, or SSL, provide some of the context as a brief history of SSL. I want to talk about how SSL can be adapted for computer vision, before finally talking about a quick experiment that I've done for today, applying self-supervised learning to a real problem. But let's start by talking about what Airbus commercial aircraft does. We're in the business of building commercial airliners, and a typical good year would build something in the order of 700 to 800 aircraft. The aircraft are assembled in what's called a final assembly line, where all of the parts that Airbus and other suppliers have made are brought together, like you can see in this video here. We're talking about fuselage sections, wings, engine pylons, the tail, which you can see here. All of these things come together and are assembled into a final product. I think this video really helps you appreciate the scale at which we operate, but we also understand the standards that are involved in aerospace. It's something where it really needs to be done right, and it really needs to be good. Now, a lot of my focus at Airbus is on the analytics pipeline. So this is looking at how we can collect data in the real world, on the shop floor, during the manufacturing process, how that data can be processed using algorithms to generate analytics, which can then power applications to help real people make real decisions. But today I really want to focus on the processing aspects of this. Now, why is self-supervised learning such an interesting area? To start with, I want to do a thought experiment. Now, I'm not an expert on children, but as far as I'm aware, they're really good at learning new things. For example, if you've got a child and you are trying to teach them something, and they might see a dog for the first time and a cat for the first time, you can go to them and say, this is a dog and this is a cat. And you can show them lots of different examples of dogs and cats. And they're pretty good at understanding that there's two distinct types of animals, and this is a class of animal called a dog, and this is a class of animal called a cat. Now, we're also probably very familiar with this application of computer vision, building a convolutional neural network which is capable of discriminating between cats and dogs. However, unlike a child, a convolutional neural network might need to see hundreds of examples of each animal to be confident and get the same level of performance as a child. So we can understand that this ability to learn very quickly from little data is really interesting for us as data scientists, because personally I hate labeling data. And it's not that I just hate labeling data, it's often there'll be situations where we have far more data than we can ever label. I want you to imagine a situation. Let's say that you work for a company and your boss comes to you and they say, look, we've got, say, 1 million images of steel plates, and some of these steel plates have defects. But we've only managed to label 1% of the steel plate. So say we've got maybe 10,000 examples, but we've got 1 million images of steel plate. In a conventional way of working, what we would do is we would build a classifier and train that on those 10,000 examples. But we wouldn't be able to leverage those 990,000 other examples that we have at our disposal, this unlabeled data. So this is potentially where self-supervised learning could come to the rescue. And I want to quickly go through some terms because I think it's really important at the outset to make sure that we're really clear about what different words mean. We've got supervised learning, which is where our data is labels. We've got semi-supervised, where only some of our data has labels. We've got unsupervised, which is where none of our data has labels. And we've got self-supervised. So our data doesn't have labels, but we engineer our own labels. But what is self-supervision? It's a form of unsupervised learning where the data itself provides the supervision. In general, what we do is we withhold some part of the data and then task the network with predicting it. The task itself defines a proxy loss, and the network is forced to learn what we really care about. For example, a semantic representation in order to solve it. So the current practice is where we'll take a network which has been pre-trained on a very large data set. So for example, we might take a model that's been pre-trained on ImageNet. What we'll then do is we'll fine-tune it on another task. So for example, we might have the challenge of building a network which can identify different types of aircraft. So for example, we might want to identify the Airbus A320, the Airbus A330, the Airbus A350, or the Airbus A380 in an image. So what we'll do is we'll take a labeled data set where a number of different examples of each aircraft is labeled, and we'll train our model on that. So what's wrong with human annotated supervised learning? Well, a large class of contemporary machine learning methods rely on human-provided labels as the only form of learning signal used during the training process. This over-reliance on direct semantic supervision has several perils. For example, the underlying data has a much richer structure than what the sparse labels can provide. We often require large numbers of samples to learn from and converge to brittle solutions. It leads to task-specific solutions rather than knowledge that can be repurposed. We also have the expense of producing a new data set for each task, and often it can be very, very challenging in some domains, for example, medical data or manufacturing, to provide enough annotation. We also have this huge untapped availability of imagery and data. So for example, on Facebook, there's 1 billion images uploaded per day and 300 hours of video are uploaded to YouTube every minute. And as I mentioned before and alluded to, probably most intriguingly, it's how infants may learn. So as compared to the traditional workflow, how does the self-supervised workflow work? Well, giving an example, let's say that we still want to build an aircraft classifier. Instead of having to label all of the images, we might have 1 million images of aircraft of all different types. What we could do is we could take this imagery, all of it unlabeled, and then use a pretext task and self-supervised learning to train a model to solve this pretext task. We could then take the weights of the network or the network that's been trained and fine-tune that on a subset of the imagery which has been labelled. So this in turn could give us superior performance than what we would have if we had if we'd used this traditional method. Turning away from computer vision for a minute, I think it's really interesting and instructive to look at the history of the field of NLP. In particular, I'm sure that many of us are aware of the huge breakthroughs that have happened over the past couple of years. Looking at this chart, we can see the huge improvement in performance that's occurred as the result of the BERT revolution. Now, BERT is a form of self-supervised learning, where the BERT algorithm undergoes pre-training using a closed passage type task. Now let's look at one of these tasks together. Here we can see a paragraph of text that's somewhat relevant to me. You can notice I've redacted some of the words. But as humans, we can infer what the words are. And this is pretty much one of the tasks that's used to help train BERT, where a paragraph of text is fed in and words and tokens are removed. And then BERT has to predict what word should go into each slot. Now, that's enough talking about NLP. Let's turn our attention to computer vision. Now, one of the challenges for applying self-supervised learning to computer vision is fundamentally there's a big difference between NLP and computer vision. In NLP, when you remove a word from a sentence, there's only a finite number of other words that could go into that slot. In the case of computer vision, on the other hand, we have millions of other images that could be generated when we remove part of another image, if we start to look at things on a pixel by pixel basis. So when you think about an image might have, 3 color channels, and there might be 256 different values for each pixel, so you can understand from a combinatorial basis just how many different other possibilities there are for what could go where. So we really have to get a bit more creative when we start looking at how we can create these surrogate proxy tasks that we want to carry out. Now, there's this really rich legacy over the past couple of years of people engineering really clever ways to come up with different tasks. So, for example, what you could do is if you've got a movie, you could reorder the frames. So then it becomes a combinatorial problem to reorder the frames. You might have an image. This is one of my favorite techniques. You might have an image where you slice and dice it up, and you've got all these different parts, and then it's like a jigsaw, so you need to rearrange them back into position. You've got other tasks. So, for example, you might decolorize a frame and then have to predict the color of the frame. So there's lots of different tasks like this that have been engineered. But really, at our core, what we're trying to do is to engineer a representation. So we might have an image which is this million dimensional vector, and we're trying to crunch it down to a representation. And what we want to do is we want to generate representations where images that are semantically similar end up with similar representations. So even if our representation was a very high dimensional vector, so a 1,000-dimensional vector, if we use a technique, say a UMAP or t-SNE, to map it down to 2 dimensions, what we would want to see is that images which are semantically similar, so on the left here you can see there's 2 images of plane, where there's different lightness in the image. On the other one you can see another 2 images of a different plane, a different situation, where one of the images has been flipped left to right and the color balance has been changed. The images of the same aircraft, semantically the same object, are being mapped to the same point in space. The past couple of years have been particularly fruitful for research. There's been a flurry of new and interesting papers that have come out. Some of the most famous papers from this period include things like SimCLR, SimScience, SWAV, BYOL, and one they'll focus on today, Barlow twins. I now want to deep dive into some of the components that you'll find in a typical setup for self-supervised learning, in particular the network, the augmentation, and the pretext task. Now really, in terms of the network, what we're really focusing on is training these convolutional filters. We're trying to learn weights and biases that will generate useful representations for our data sets. So what I mean by this is that we feed in imagery, and then we want to try and learn the different concepts so that similar things, similar concepts will be mapped to similar points in a much lower dimensional space. So really we've got this form of dimensionality reduction where all we need to do is learn these filters so they give us the best possible representations. Now, while the network itself that we're training might be something fairly standard, like a ResNet 50, Where it becomes really interesting is in the pretext task, and this is where a lot of the creativity comes in and where a lot of the research has been done. There's a number of different state-of-the-art methods, including contrastive learning, different Siamese architectures, and redundancy reduction, which is Barlow twins, which I'll talk about in a little bit. Now, all of the different papers I've mentioned have different strategies that are underpinning them. I don't have the time to go into each of them because there's a lot of complexity that's involved, and really we're at the stage where we're learning what works and what doesn't work, and we're really looking for that silver bullet for a solution that's simple and works well. Now, I'm not sure if Barlow twins is that silver bullet, but it's certainly very promising, and it's beautiful in its simplicity, so let's now focus on that in more depth. At a high level, what we do is we start by drawing a batch of images, let's say 24 images. We then augment this batch twice, so we'll generate, say, an A batch with one set of augmentations and a B batch with another set of augmentations. They're different. What we then do is we feed each image in the batch through our ResNet 50. We then, at the end of our ResNet 50, and sorry, just to specify, this is what's known as the Siamese network. So we've got two identical networks that are linked together. The weights are identical and the biases are identical. On top of the ResNet 50, we've got an MLP that generates a representation, which you can see here marked as representation ZA and ZB. What we then do is for all of the images in the batch, we compute the cross-correlation, and I'll go into more detail later how this is done, between the representations of all of the images in the batch. Now, ideally what we want is we want to generate representations with minimal redundancy. What that means is that for the two matching images that are fed through our Siamese network but have been differently augmented, we want to generate identical representations. But we want the representations for different images in the batch to be as different as possible. But really, why is this important? Why are we doing all this with the cross-correlation? Why do we want there to be as little redundancy as possible? Well, one of the challenges is if we're trying to train a network to generate the same representation for the same image, what can go wrong is that the network could learn that it can get a very, very, very low loss just by mapping every single image to have the same representation. We have this collapse. So in summary, the aim is to make the outputs as close as possible to the identity matrix, and we want to minimize the redundancy between the different vector components. Why is this important? Taking a quick thought experiment. If we only wanted the network to learn that different inputs, differently augmented input images should have the same output vector, what could happen is the network could learn to map all images to the same output vector. So what this means is we'd have a really low loss. And this is something that can happen with earlier different networks that were explored in some of the other papers. So for example, SimCyan. Now I want to talk through slowly and in more detail. So as I mentioned before, what we do is we draw a batch of images. For each image in the batch, we augment it twice in two different ways. We then feed it through for example, a ResNet 50 network. And what we do is we generate a dense representation, so a vector, from our input image. We've got two different networks which are both identical. So this is our Siamese network. What we then do is that for each image in the batch, we generate the cross-correlation of its vector representation. Now, if you're unsure what cross-correlation means, here's a very, very quick example. What we do is we compute the dot product between each combination of vectors, and then we normalize that. So basically what we do is if we've got two vectors, A and B, and we want to compute their normalized cross-correlation, what we can do is we compute the dot product, and then we divide by the length of A times the length of B. What's beautiful about Barlow twins is its simplicity and its elegancy, but it's also incredibly effective. Let's take the situation of trying to train on ImageNet, where we've got 1,000 different classes. What happens if we try and train a supervised model on only 1% of the class, on only 1% of the data? Well, we see that we get an accuracy using a state-of-the-art model of about 25%. Using Barlow twins, pre-training on all of the data without the labels, and then fine-tuning on that 1% of the labels gets us to 55% accuracy. What if we train on 10% of the data? Well, using supervised learning, we get 56% accuracy and 70% accuracy for Barlow twins. Now I'm going to finish by talking about some of the experiments I've done. One of the experiments in particular that was really interesting was applying Barlow twins to the fine-grained visual classification of aircraft datasets. This is a really interesting dataset because it's got 10,200 different images of 102 classes, where each class has 100 examples. Basically, it's photos of different aircraft types taken by photographers. What's really interesting about this data set is that it's fine-grained. So, for example, we might have the Airbus A319, Airbus A320, Airbus A321. So these are all aircraft that are made in the same factory. They're very, very, very similar in appearance. In fact, the only difference for them is the length of the aircraft. So this is particularly challenging when we're trying to train models to discriminate between these aircraft when the only difference between them is their length. Now I'm going to start off by presenting the results, which I think are really interesting. The comparison I'm making is between a network that's been fully supervised on a data set and one that's undergone self-supervised pre-training. So basically what that means, just to remind you, is here on this graph you can see I've done different experiments where I'm taking some proportion of these 10,200 images and I'm providing them to the supervised network to learn on. In the case of the self-supervised pre-training, what I'm doing is I'm giving it all access to all of the examples but unlabeled, and then I'm fine-tuning on the same number of examples that I provided to the fully supervised network. The key here in this case, and the reason why self-supervised learning does so well, is that I'm using random initialization for the network. Now, when I talk about random initialization, what normally happens, or what we'd normally do a lot of the time in a lot of problems, is that we can use transfer learning. So this is where we would have a model that's been trained on something like ImageNet, and we would take those weights, we'd take those biases, and we would transplant them and then fine-tune or adjust them to a new situation. But often what can happen is we can be in a situation where we have a very different data set, or we could have something where we've got a different number of color channels, so we can't really adapt the ImageNet dataset, and that doesn't really help us, and we need to use random initialization. Now that you've seen where we got to, I want to talk about how we got there. Here what you can see is after we've trained Barlow twins, I did a test. Now I mentioned before that our network takes an image and generates a vector, and similar images semantically should generate similar vectors. And what I've done here is I've done a k-nearest neighbours query. So the image on the far left, I've looked for other images with similar output vectors to the image on the far left. And here immediately we can see something has gone wrong. What we were hoping for is a network capable of clustering similar aircraft types together. Now we can see that it looks like the aircraft type has been matched correctly, but when we actually look at the images for a little bit, we realize that what we're matching on isn't the aircraft type, but rather the color in the imagery. How do we get around this? Well, a simple solution is to use augmentation to define invariances. What do I mean by this? Well, when the images undergo augmentation, essentially what we're doing is we're telling the network, okay, image A and image B are semantically the same for that augmentation. So for example, if we get an aircraft and we flip it left-right, the network will see aircraft that turn to the left and aircraft that turn to the right, and they'll be told that they're the same aircraft. So what this will do is it'll ensure that we don't end up in a situation where it thinks that an aircraft pointed towards the left is semantically different to an aircraft pointed towards the right. Another thing we can do is convert all of the images to grayscale. What this means is that it'll lose any information about the colour, and it can no longer semantically cluster and is no longer rewarded for semantically clustering images according to their colour. Now, with this enhanced augmentation scheme, we get some really interesting results. If we look at these images and look above them, we can actually see there's a class label. What's particularly interesting here is that while 54 and 8 are different classes, the aircraft that you can see there were designed by the same manufacturer. In terms of representation, a really interesting representation has been learned. If we take all of the vectors that have been generated, so 1,000-dimensional vectors, one per image, and then we use UMAP to bring that down from, say, 1,000 dimensions to 2-dimensional space and cluster, we can see there's two distinct clusters. And what's really interesting here is there's one cluster for aircraft that are flying and another cluster for aircraft that are on the ground. Now, while experiments are interesting, I really want to talk about how we can use self-supervised learning at Airbus. I see a number of different opportunities that are really interesting. In particular, we've got shop floor. So this is where we're installing cameras into our final assembly lines to digitize what's happening. The challenge here is that we can collect huge volumes of data, but it's very difficult to label all of it. So self-supervised learning gives us the opportunity to develop better models that can leverage these huge volumes of data that we've collected. Other areas of interest include quality, because often when we're assessing quality use cases, we're also collecting huge volumes of data. There's other areas like airline operations, so this would be offering new concepts and services to airlines to improve aircraft turn performance, on-time performance and things like that. There's the huge volumes of data we collect as part of aircraft flight test campaigns. And finally, documentation. So this is where we have millions of documents that have been generated over the past 50 years of the company, and they've been digitized, but it's very hard to leverage them because they've been digitized from an analog format. So self-supervised learning provides the opportunity to convert them into a digital format more accurately. So, if self-supervised learning is practical, how would it change our strategy? Firstly, it would incentivize us to collect more data. Secondly, to retain more data. And thirdly, to really focus on our data and model management. In fact, it really helps us focus on the fact that many people talk about data being the new oil, but I think for a long time that hasn't really been true, in the sense that you haven't been able to transform this data into something useful. But self-supervised learning really gives us this opportunity now to leverage all the data we've collected, and that's why I think it's so exciting. Thank you so much for your time. It's been an absolute pleasure to present to you.